Hello and welcome to this video lesson on complex ions. You may remember in the last video lesson we referred to several of the chemical characteristics of transition metals, one of which was that they could form complex ions in solution. And so what we're going to do in this video lesson is go through complex ions in a bit more detail. So our learning objectives for this video lesson are, firstly, we're going to learn what are complex ions, and then we're going to look at a species called ligands. We're going to find out what they are, and then we're going to look at complex ions, and in the middle of a complex ion is going to be a metal ion, and we're going to work out the oxidation state of that metal. And also we're going to have a look at the shapes that complex ions form and how this depends on their coordination number. So of course we'll have to learn what coordination number is as well. And lastly, we're going to have a look at hemoglobin and why that's relevant to a lesson on complex ions. Okay, so let's start off with our definition of complex ions. So a complex ion is a metal ion surrounded by coordinately bonded ligands. So it's a metal ion surrounded by coordinately bonded ligands. Okay, so let's unpick that. Of course, you know what a metal ion is, and so it's surrounded by coordinately bonded ligands. So first of all, let's remind ourselves what a coordinate bond is. So a coordinate bond is a bond where both of the bonding electrons, so it's a covalent bond, so both of the bonding electrons are provided by one atom. Both electrons provided by one atom, and it's denoted by an arrow, whereas a normal covalent bond might just be this straight line without the arrowhead on it. Okay, so that's a coordinate bond, also called a dative covalent bond. You might be familiar with it under that name. But that still leaves us defining ligands. So what is a ligand? Well, the ligand is an atom or an ion or a molecule that provides that coordinate bond. So it provides the pair of electrons. Provides the bonding pair. Of electrons. Okay, so that's what a ligand is, and to make that clear, why don't we have a look at an example. So here's a picture of a copper complex with surrounded by water molecules. So the central metal ion, you see here that I'm underlining, is a copper 2+ ion, and it's the water molecules, 6 of the water molecules surrounding it, acting as the ligands. So let's just label our so the ligands are the water molecules, and these are the coordinate bonds. Let's draw a little arrow coming back here. So this is the coordinate bond. Because both electrons provided by the oxygen atom of the water molecule. Because oxygen in a water molecule has 2 lone pairs of electrons, and so one of those lone pairs is offered up as the coordinate bond to the copper 2+ ion. So that's what a complex ion is. It's usually a transition metal, in this case copper 2+ ions, and it's surrounded by ligands, in this case water, and they are ligands because they are providing, their lone pair is providing the bonding pair of electrons that forms a coordinate bond. Okay, so that's what complex ions are. Right, so we've defined what complex ions are, and we've sort of looked at what ligands are, but there are actually different types of ligands. So we're going to have a look at the several different types, 3 different types of ligands that we're going to know about. Okay, the first type of ligands that we're going to look at are called unidentate ligands. And they are ligands that can only form one coordinate bond, and they're called unidentate ligands. So usually the ligands are unidentate if they have only one lone pair of electrons, in which case that lone pair becomes a coordinate bond, and if they've only got one lone pair, they can only form one coordinate bond, and so they would be unidentate. There is an exception, which is the water one that we looked at before. So let's draw a few examples just to make sure that's all clear. First of all, let's draw ammonia. So ammonia, you know, is NH3. Okay, so let's draw ammonia in the middle in green. And it's bonded to 3 hydrogens. We'll put the hydrogens in blue. And nitrogen has a lone pair of electrons, and let's draw that down here like this. So it has a lone pair of electrons. So as you know, it has 5 electrons in its outer shell. 3 of them are involved in the 3 covalent bonds with the hydrogens, and the last 2 are left as a lone pair, which are drawn there as a couple of dots. All right, so you can see it's got one lone pair, and therefore it would be able to form one coordinate bond, and therefore clearly that is a unidentate ligand. Okay, so let's have a look at chloride. So chloride, Cl-, and how we'll draw that is we'll just put chloride minus with a lone pair here, and let's just talk through why that's got one lone pair. So chloride, group 7, 7 electrons in its outer shell, but you see it's a chloride ion, so it's gained an electron from somewhere, so that means it's got 8 electrons. But 6 of them are otherwise occupied, so it's got one lone pair. And water molecule, let's draw the water molecule. So we've got our oxygen bonded to a couple of hydrogens. As you know, oxygen, 6 electrons in the outer shell, 2 of them are occupied in these 2 covalent bonds, and so it's got two free lone pairs, which we'll draw like this. But because they are so close together in water, they can only form one coordinate bond. So water is actually a unidentate ligand. So that was the first type of ligand you need to know about. The second type is multidentate ligand. So these are ligands that can form more than one coordinate bond, and they're called multidentate ligands. And here's an example of one. It's called EDTA, which is known as ethylene diamine tetraacetic acid. So let's just write that down as EDTA. EDTA, and that's widely used as a limescale remover. So if you've got a tablet of solid that you might put into a washing machine to remove the lime scale, or even a coffee machine, it's likely to be EDTA that's being used. And this is a multidentate ligand, so let's highlight the lone pairs. So the two nitrogens have a lone pair that could become a coordinate bond and attach to a metal ion, and the oxygen on the carboxylic acid groups, there's 4 of those, tetraacetic acid. So you've got 4 spare lone pairs there. So that makes 6 in all. So you could actually call this a hexadentate ligand. Hexadentate ligand. Okay, so that's multidentate. Let's have one more example. And that would be a bidentate ligand. Yeah, so a bidentate ligand, as you might guess, is a ligand that can form 2 coordinate bonds. An example would be ethane 1,2-diamine. So let's have a look at ethane 1,2-diamine. So first of all, let's write it out. Ethane 1,2-diamine. And that is an H2. And then it's eth, so we've got CH2, CH2. And it's diamine, so we've got another NH2 on the other end of the molecule. So that's what ethane 1,2-diamine looks like. And our lone pairs are on the nitrogens, of course. I'll just draw them like that. So our lone pairs are on the nitrogens, and of course the hydrogens and carbons don't have lone pairs. So they are our 2 lone pairs that are available to form coordinate bonds, and there are 2 of them, and that's why ethane 1,2-diamine is a bidentate ligand. So what I want to do now is I want to draw how ethane 1,2-diamine forms its complex, because it's slightly different from the previous 2 we've looked at. So let's just write an M in the middle for our transition metal ion. We'll put that in black. So in the middle we've got our transition metal ion, and that's got some charge. I won't write the charge because it could be anything. And then we're going to have a look at how ethane 1,2-diamine surrounds this metal ion. And actually 3 of these molecules surround it. So the first coordination bond comes out of the nitrogen, so I'll draw my there, and it is, so the NH2 group, I won't draw the hydrogens and I won't draw the carbons, but what I will try and draw is black lines for the bonds. So this would be a carbon, that would be a carbon, there'd be a couple of hydrogens there, and then at the other end of the molecule you've got another nitrogen, and that would actually be behind the page, and so behind the page, and it would be facing towards the metal ion. So I've drawn it in a dotted line to show that the coordination bond is really coming from back behind the plane of the slide into the metal ion, which is on the plane of the slide. So that's how we would get our first 2 coordinate bonds from our first molecule of ethane 1,2-diamine. But actually this metal ion is very positively dense as far as charge is concerned, and so 3 of these molecules can surround it. And so the next one would also come from outside, from behind the page, and form a coordinate bond like this, and it might look something like this, where this nitrogen that I'm just drawing now is actually out of the page towards you as a viewer, and the bond would come out of the page and go back towards the metal ion in the middle there. So I'll draw it as a solid sort of triangular arrow like that. And that would be the second one, and the third one would fit in like this. So the other nitrogen of the ethane 1,2-diamine would be directly below the metal ion, and the bond would be in the plane of the slide, vertically up towards the metal, and we would have our carbon chain like this, connected to our other nitrogen. Oops, that should be in green. So our other nitrogen's here with its lone pair, and it also is out of the page, and it's coming back. The bond is forming back towards the metal ion like that. So that's that last one is supposed to be out of the page, bonding away from us back towards the metal ion. So here you can see that we've got one metal ion, but three ligand molecules, each of the ligand molecules providing two coordinate bonds, and so the total number of coordinate bonds is 6, and that's going to lead us on to explaining this concept of coordination number. So that's an important definition, so let's write it down. So coordination number. So this is the number of coordinate bonds that are formed with the central metal ion. So there we are. So in this case, coordination number was 6. So I'll just draw a little arrow here, coordination number 6. So, and that was 2 per molecule and 3 molecules. Okay, so let's reflect back on the 2 previous complex ions that we looked at and see what their coordination numbers were. Yeah, so if you remember right at the start of this video lesson, we looked at a hydrated copper complex like this, with a copper ion right in the middle, surrounded by 6 water ligands, each providing 1 coordinate bond. And so the coordination number of this is going to be 6. So first of all, let's label it. We've got a hydrated copper complex, and in fact, if we wanted to write its formula, we'd write Cu H2O6, and it's got a charge of 2+, because the water molecules are neutral and the copper ion is 2+. So that's a hydrated copper complex, and its coordination number is 6, and that's 6 molecules, 6 ligands times 1 bond each. Okay, so that was one of the complexes that we looked at, and another one, we remember the EDTA molecule. Well, when it surrounds a metal ion, this is the way that it does it. So this is one, apart from the M bit in the middle, that's one EDTA molecule. So you'll remember that we had 2 nitrogen lone pairs and 4 lone pairs on 4 of the oxygen ions, charged atoms, and that's the way that they surround the metal ion. So 2 bonds are formed from above and below, and then you've got 2 bonds coming from where we are looking into the screen, and then another 2 bonds coming from behind the screen back towards the M. So that coordination number is also 6. Let's label it first, EDTA. And this coordination number is also 6, but that is 1 molecule times 6 coordinate bonds in that molecule. But the coordination number ends up being the same. Okay, so there's a couple of examples, and our coordination number previously was, or in the previous slide, was also 6, provided by 3 molecules, each of them being bidentate ligands, i.e. giving 2 coordinate bonds each, 2 times 3 being 6. So let's just check where we are on our learning objectives. We definitely understand what complex ions are, and we've very thoroughly been through all the different types of ligands. So now that leaves us to go on with working out the oxidation state of the metal ion in the complex. So the oxidation states of complex ions, here's the rule. So the oxidation state of the metal ion, right, is the total oxidation state of the complex minus the sum of the oxidation states of the ligands. There we are, there's the rule. Shall we do a couple of examples to make sure that's clear? First of all, the easy one that we did before, which was the hydrated copper complex. So we had H2O with 6 water ligands surrounding a 2+ copper ion. And let's just apply our blue rule to this complex here. So the oxidation state of the metal ion, that's what we're interested in, is the total oxidation state of the complex. Well, the total oxidation state of the complex is 2+. That's this 2+ here, minus the sum of the oxidation states of the ligands. Right, so the oxidation state of the water molecules, which are the ligands, is 0. Okay, so we have oxidation state of copper, so copper equals 2+ minus 0. So our oxidation state of our copper is 2+. Okay, that's the first example. Let's do another example here. So let's say we had an exam question which said, what is the oxidation state of cobalt in cobalt chloride? So let's say cobalt in a cobalt chloride complex. So that's how we're writing the cobalt chloride complex, and we want the oxidation number of our cobalt in that cobalt chloride. Okay, so applying our rule that we wrote out in blue, the oxidation state of the metal ion is, let's do that in red again, is the total oxidation state of the complex, so that's 2 minus, and it's minus the sum of, right, so we'll draw a little bracket, so the sum of the oxidation states of the ligands. So each of the chlorides, and there are 4 of them, each of the 4 chlorides are -1. So that's 2 minus -4. Sorry, -2 minus. -2 minus -4. I forgot to put the minus in there. Okay, so we've got -2 minus -4 is +2. And so the oxidation number of cobalt in cobalt chloride complex is +2. So good, now we have quickly done our first 3 learning objectives, and now we're going on to shapes. What shapes do these complex ions form, and how does this depend on their coordination number? And while we're here, let's just say that at A level we deal with coordination numbers 4 and 6 mostly, with the odd coordination number 2. So we've got coordination numbers 4 and 6, mostly 6, bit of 4 and the odd 2. So let's start with the most common shape, and that's the shape that is formed for a coordination number of 6. So complex ions that contain 6 coordinate bonds have an octahedral shape, and we've got 3 examples of those here. The first one on the left is a hydrated iron complex, so let's just write the formula of that out. So we've got iron with the ligand being water. We've got 6 waters, and the overall charge on the complex is 2+. So that must be Fe2+ in the middle there. So that's what we've got there, and that is called an octahedral shape, where, look at the shape of these arrows, the coordination bond arrows, where the 2 triangular arrows are water molecules out of the page towards us, bonding in towards the iron, which is on the plane of the slide. And then we've got 2 dotted arrows, and they are representing water molecules from behind the plane of the slide, coming forwards towards the iron. And then we've got 2 more ligands, one on the top, one on the bottom, both in the plane of the slide. And so you can see that is an octahedral shape. And it's the same shape for the other 2. So in the second complex, or the middle complex, we've got a cobalt ammonia complex. So let's write that down. We've got cobalt, and we've got 6 ammonia ligands, and the overall charge on that complex is 3+. And because our ammonia is a neutral molecule, then it must, all those 3+ must come from the cobalt ion. So that would be a cobalt 3+ ion. And by the way, they're both aqueous, as is the third. But also because, now this is interesting, where in the third one, where you have both ammonia and water ligands, and they're both roughly the same size. So this is actually worth writing down. So water ligands and ammonia ligands are both small compared to the size of some of the other ligands that you can get. So they're both small, and therefore you can fit 6 around the metal ion. And so that's what leads to the octahedral shape. Now, if they were larger, if the ligands were larger, like a chloride ion, for example, then you wouldn't be able to fit 6 chlorides around a metal ion, and so that would be a different coordination number of a complex. Okay, just finishing off this slide here, we'll write the formula of the last complex down. So it's a copper complex, and we've got 4 ammonia ligands, and we've got 2 water ligands. And so we write that down like this, with an overall charge of 2+. So again, the water molecule and the I forgot my little 3 in there from our ammonia. The ammonia molecule are both neutral molecules, so that 2+ charge for the complex is the same as the 2+ charge on the copper ion. So that's the most common shape, that octahedral shape, where you've got 6 coordinate bonds. Let's look at complex where you've got 4 coordinate bonds. And when you have complex ions that contain 4 coordinate bonds, coordination number 4, they usually have a tetrahedral shape. And the tetrahedral shape looks like this. So we've got a couple of examples here. So we've got a copper chloride complex, the chlorides each having a 1- charge. And we've also got a cobalt chloride complex. And notice the copper one is yellow and the cobalt one is blue, and so we'll come on to colours in a future video lesson. But for now, just notice the shape and see how the shape's drawn. Now the triangular arrow is trying to represent that chloride ion that is out of the slide, nearer to us as we look at it, bonding back towards the copper. And the dotted line for the chlorides is from behind the plane of the slide, bonding back towards the copper ion. So you can see that shape there, and that's how we draw that shape, that tetrahedral shape. Perhaps in class we'll get the Mollymods out and just practice seeing it in 3D. Anyway, so that's the usual shape for a 4 coordinate bond complex. And notice that these ligands are all chlorides. And remember what I said about chloride as a ligand. It's a large ligand, and we can't fit 6 around there. We can only fit 4 around there, and that affects the shape of the complex ion and usually makes it a tetrahedral shape. But not always. Let's have a look at the other possible shape for a 4 coordinate bond complex. So the other possibility for the shape of a coordination number 4 complex ion is a square planar shape. Square planar shape, when we've got 4 coordinate bonds and some of the ligands are large, we get a square planar shape. So an example would be cisplatin, and the formula of cisplatin is we've got platinum, and you've got a couple of ammonia ligands and a couple of chloride ligands. And that's the formula of cisplatin, and it has a square planar shape and looks like this, and with the large chloride ligands coming out of the page back into the platinum ion, and the 2 ammonia ligands behind the plane of the slide coming back in a square shape. So that's the alternative, although a bit rarer than the tetrahedral shape that we get for coordination number 4. So I should have mentioned that cisplatin is a chemotherapy drug. Okay, and the last shape that you need to know is just a linear shape, just in a line. When the coordination number is 2, we have 2 coordinate bonds, and an example of that might be tolerance reagent. So let's have a look. Some silver complexes have 2 coordinate bonds in a linear shape, like Tollens reagent. So let's write that out. So Tollens reagent is you've got a bit of silver ion, and you've got that surrounded by 2 ammonia molecules, and it's got 1 plus. As usual, the silver ion is just 1 plus ion, and that forms a linear shape. So let's draw that out. So you've got your coordination bond on your nitrogen and your 3 hydrogens attached to the rest, with making up the rest of the ammonia molecule. So that lone pair makes your coordination bond. That's bonded into a silver ion in the middle, and you've got another lone pair coming off the nitrogen of the other ammonia molecule. And so that looks like that, and it's just in a line, a straight line like that. So that's called a linear shape. And Tollens reagent, you might come across that, especially in biology, testing for aldehydes, and that's the formula of it, and it is a complex that makes a linear shape. So let's just have a quick check where we are on our learning objectives. We have already checked that we've done the first 3, and now we know the shapes of the complex ions. So we've got octahedral, we've got tetrahedral, and we've got linear. And let's not forget a square planar. And the coordination numbers, this one was 6, this one was 4, this one was 4, and this one was 2. So there are shapes for our complex ions, and whether it's a tetrahedral or square planar depends on the size of ligand. Smaller ligands, tetrahedral; larger ligands like chloride, square planar. Okay, so there we have shapes all done, and last thing to do is to consider what is hemoglobin. So as you probably know, hemoglobin is a protein found in the blood that helps to transport oxygen around the body. And here's a picture of some red blood cells which are full of hemoglobin, making them red. And so let's look at the complex ion that is hemoglobin. So in the middle of the complex ion is an iron ion. So let's draw our Fe in the middle there. And what we have is we have a ring, which is called a porphyrin ring, of nitrogen atoms that are part of a heme molecule. So let's switch to green, and so you've got this nitrogen at the back. So imagine these 2 nitrogens are behind this plane of this slide, and they're forming bonds towards the ion Fe2+, and these 2 nitrogens with their lone pairs are out in front of the screen, and so they are bonding back towards the ion like that, and they are in a plane that is horizontal, and so that plane, they form like a circular ring, and that's called a porphyrin ring. A porphyrin ring. And this is the part of the molecule that is called heme. The part of hemoglobin that is called heme is this part here. And then the globin part of the molecule is coordinately bonded to the ion, from below, and that also has a nitrogen atom on it with a lone pair that provides the electrons for the coordinate bond. And then we're not going to write the whole globin molecule, it's too big, so I'll just write it like this. So that's the globin molecule, and that's the protein, and together they form hemoglobin. So you can see that so far we have 5 coordinate bonds attached to this iron, but it is this iron 2+ ion is hexa-coordinated. It likes to have 6 coordinate bonds, and the 6th one is for either oxygen or water, depending on where it is in the body. So if this hemoglobin molecule is in the blood, which is in the lungs, then the lungs have a high concentration of oxygen, and so oxygen molecules, so O2 molecules with their lone pair, not drawn that very well, but that blob that I've just drawn is supposed to be a lone pair of electrons, and they provide the 6th coordinate bond for the iron, because iron is hexa-coordinated. And then the blood goes around the body and ends up in a place that is short of oxygen, so let's say a muscle cell, and the concentration of oxygen is low because it's already been used up by contracting, and so the concentration of oxygen is low and the oxygen leaves. But respiration, of course, produces water and carbon dioxide, and the water is carried away. So when the hemoglobin is in the muscle cell, where there's a high concentration of water, the oxygen has left, and the water molecule forms that 6th coordinate bond and travels with that hemoglobin molecule through the blood and back towards the lungs, where it can leave through the lungs and be replaced by an oxygen molecule again, and that process repeats. So that's the hemoglobin complex, and very briefly how it transports oxygen from the lungs to the muscles and water from the muscles to the lungs. So that's a bit of how science works as far as complex ions is concerned. And that's about it for this lesson. We will just finish up with a review of all our lesson objectives. And here they are. So already we have checked off that we've done all of these, and now we also know what hemoglobin is. So hopefully that has been clear and thorough, and if you have any questions, as usual, post them on the chat room or come and see me.